So first we have Andrew Poelstra. He's the director of Blockstream Research, which is a team of cryptographers, Bitcoin developers, and network engineers with extensive research working on the Bitcoin protocol. He's invented several privacy and scalability technologies in the Bitcoin space, including confidential transactions, Taproot, Miniscript, multi-sig, and scriptless scripts. And I had the honor of working with him for several years at Blockstream. So welcome, Andrew.
Thanks, Chris. Yeah, thank you for that introduction to me and to Blockstream Research. Yeah, so here I'm at Blockstream Research. We sort of do two things, right? We do cryptography, in particular, focused on signatures and variants of signatures, and we work on like smart contract language design kind of stuff. So I'm going to talk today is more on the signature side of that project we've been working on for a few years called anti-exfiltration. So let me explain what that is, what the problem it solves, and how we've implemented it, basically. So I'm going to try, so the guidance from Chris was that I should try to talk for maybe 15 or 20 minutes of monologuing. And of course, you're welcome to jump in and ask questions, bearing in mind, I guess your voice will be on the recording. And then once I'm done my monologue, then we'll have 15, 20 minutes of Q&A and kind of go from there. So I'm going to try to give a high-level picture of everything. I've got a couple very dense slides near the end I'm just going to skip over. And hopefully we can, yeah, we'll just go from there. So I'm having some Zoom permission issues with my screen sharing. So Chris, if you could put up my slides, that would be super helpful.
Okay. It says that I'm sharing it.
Okay, cool. Let me turn off my video. Okay,
we are on EC signatures.
All right, perfect. Cool, there we go. So let me jump into this. So, yeah, I thought it might be funny to open the first talk of the morning with a bunch of equations, but I'm going to try to keep this high level, at least mathematically high level, and this is the only equation I'm going to show. And I'm not even going to dive too much into this. So what I've drawn here is the equation for a Schnorr signature. And what I want you to take away from this is not, what this exact formula is or what the plus and the time symbols mean, because they're not necessarily familiar operations, but that you can think of an EC signature, either ECDSA or Schnorr, as being a linear equation in two pieces of secret data. So the idea here is that you have a one piece of secret data is like your actual secret key, right, which corresponds to your public key, and that's a permanent piece of data. And then for your signature, you generate also an ephemeral, what we call as a nonce. And yeah, that matches my equation. Thanks, Jesse. A nonce, which is sort of, you can think of it as like an ephemeral key. And the premise here, right, is that every signature is going to represent an equation. And you may remember from your grade 9 linear algebra that if you have a system of linear equations, oh, perfect, Chris, if you could scroll now. A system of linear equations, if you have as many equations as you have unknowns, then you can solve it. But if you have more equations than unknowns, you might not be able to, because there might be no solution. There's just the equations are inconsistent. And if you have fewer equations than unknowns, then you also can't solve it, this time because there's an infinity of possible solutions. So here we're working in a finite field, so it's not actually infinity, but the idea here is that as long as every equation we publish, every signature we publish, comes with another unknown, so there's always one more unknown than equations, then nobody can extract your secret information, because there's 2 to the 256 roughly possible solutions, and all of them are as good as any other. They can't distinguish, the real one that's your key from anything else. So this is the idea behind these nonces, right? Your signature is supposed to somehow use your secret key. We need to stick some other random object in there so you have an extra secret unknown. The issue, of course, so one initial immediate consequence of this is that if you don't generate a new nonce, if you reuse a nonce from a previous signature that you used, well, now you've got 2 equations, 2 unknowns, right? Somebody can just invert the matrix, solve it. It takes, a nanosecond. You can do this a direct computation. So lots of people are familiar with the maxim that you shouldn't reuse nonces when you're producing EC signatures, because otherwise that's a catastrophic failure. And relatedly, you also shouldn't use 2 nonces where the nonces are related by like a known offset or something. So what's a bit less obvious is that even if you don't reuse your nonces, even slight deviations from randomness, like maybe like your second bit is 0 more often than it's 1, for example. If you have enough signatures, you can use these lattice techniques, which date back to the early 2000s. And Nadia Henninger and Joachim Breitner actually implemented this in 2019 and published a paper. They were able to extract a bunch of secret keys from signatures on the Bitcoin blockchain, exploiting just these nonces that were not uniformly random. And then a final point is that if you use, HMAX or other clever tricks, you can actually bias these nonces or even reuse them in a way that only a specific attacker who knows the key to the HMAC is able to observe the bias and able to extract stuff, whereas anybody else trying to do what Nadia and Joachim did will fail. It will look uniform to them. So the moral here is that it's absolutely essential that your nonces are generated uniformly at random. And the problem that we're going to try to solve throughout this talk is that if a hardware wallet is generating the randomness, then the user doesn't really have any way to verify this, right? Because from the user's point of view, the hardware wallet is a black box producing signatures, right? I mean, so if you think that your nonces might be biased, I guess you could try to like break your signatures yourself, but short of doing that, you don't have a lot of options. So let's jump into a few different solutions to this issue. So first off, the standard solution to these kind of nonce choice issues is something called RFC 6979, which is a way of producing deterministic nonces. The idea is that you have some sort of hash function, you put your secret key in, you put your message in, and then you generate your nonce that way. And if you're using a hash function like SHA-2, which empirically appears to have uniform output, then that's great. You're never going to reuse the nonce because you're always putting the message that you're signing into the nonce input. So as soon as you change the message, you completely change your nonce. You're never going to have bias unless SHA-2 turns out to be horribly broken. And RFC 6979 actually does a little bit more. It does a whole PRNG construction to try to save you even in that case. So that's great. So if you're reading like nonces can be biased and then you lose your keys and kind of panicking a moment, well, we have a solution, right? Which is these deterministic nonces. The problem with this for our purposes, of course, is that as a user of a hardware wallet, the hardware wallet's a black box, and maybe they're using 6979, maybe they're not, and there's no way for you as a user to tell, short of, again, extracting keys somehow from the wallet, which maybe shouldn't be possible, but maybe you restore it from a backup, doing a bunch of algebra and like reproducing the signatures, and then seeing whether it happens to match the deterministic algorithm that you expect is. And if you're not using 6979, if you're using an ad hoc scheme, or if you're feeding ephemeral randomness into this, which is a good idea for other reasons, like it's hopeless, so you can't verify it. So let's move on from there. So then in the crypto world, whenever you have a problem that looks like, somebody can't verify something without getting a bunch of secret data, without having access to secret data that you don't want them to have, there's kind of a standard solution, which is let's throw a zero knowledge proof at it, right? So a zero knowledge proof, for people who don't know, is a cryptographic construction where you are able to prove that some statement is true. For example, the signature was generated using a particular deterministic nonce algorithm without revealing any of the inputs. So you don't reveal your secret key, even though that went into the nonce construction. You don't reveal your secret nonce, even though it came out as a nonce construction, right? Like you keep it all private. This is great, but until 5 or 6 years ago, like this is actually like the punchline of a joke to just throw ZKPs at it. And the reason being that zero knowledge proofs are very expensive to produce. They require some pretty elaborate cryptography. The implementation is complicated, all sorts of things. And today, thanks to a tremendous amount of research from the various people in the cryptocurrency world, it's now practical actually to produce these on consumer commodity hardware, which is really cool. As that's like, nobody would have imagined that would be true 10 years ago. And even 5 years ago, it was surprising and not possible. But it's still pretty complicated. These things are still pretty expensive to compute. And if you're on a limited hardware budget, like a hardware wallet is likely to be, or if you're on a secure element or something, it's still probably not practical to produce these. And then there's another issue, which is that the zero knowledge proofs themselves work in much the same way that these signatures work. where you have some kind of permanent secret data that you're trying to protect, and you protect it by throwing a bunch of ephemeral random data at it to blind it. And so the ZKPs themselves actually have nonces, right? So if you produce a signature and then a ZKP that your signature was produced legitimately, well, if you don't have a ZKP that the ZKP was produced legitimately, right, then you've got kind of this infinite regress going on, which exactly nonces all the way down. So this, I mean, this is worth something, right? I mean, the ZKP doesn't go on the blockchain, but you know, it's not great, right? We would like to have a better solution, right? We'd like to have something that's more efficient and that doesn't have its own nonces. So one solution that's kind of a neat idea is to say, well, suppose, and we're going to suppose for the rest of this talk that the host computer and the hardware wallet are not simultaneously compromised, because they're both compromised by the same person, right? Kind of all bets are off, right? They can collude and bias nonces no matter what you're trying to do. But the idea behind this premise here is that maybe if the host had its own key and the hardware wallet had its own key, then the two of them could produce a multi-signature. And the way that EC multi-signatures typically work is that the two participants kind of combine their keys at key setup time, and then they combine their nonces at signature signing time. And the result is that both parties contribute some randomness to the nonce. So if one party is trying to bias it, well, the other party's randomness will erase that bias, okay? This is actually a pretty cool idea, but it requires the host to somehow have a key, and a typical Bitcoin workflow involves a hardware wallet having some sort of seed, right? Some sort of seed phrase or something, and deriving all of its keys deterministically from that. So the idea is that if you have the seed phrase backed up, you can always recover your keys forever. And then you can kind of generate an infinite stream of keys that any other hardware wallet can reproduce. So yeah, and Marie points out you could also do this with a second hardware wallet. And again, there are also benefits to this, you know, regardless of nonce bias, right? If you have two hardware wallets, you know, if they're compromised in any way, if one of them is compromised in any way, but you're doing a multi-sig with two hardware wallets from different vendors, right? You can protect against that. Not a bad idea, but multi-signatures, well, as soon as you have two key streams, now you have twice the key management issue, right? You've got more than one thing to back up. If you're doing it with two hardware wallets, your user has to purchase two hardware wallets. And then it's just the protocols and stuff are not so mature. And there's some implementation complexity to this, right? And as a final thing, if you only have one hardware wallet and you're trying to use a host as one side of this, then, well, hosts are not most computers are generally not designed to store cryptographic material in a way that's protected from the long term and protected from being lost and so on. A variant of this is that instead of using a real, you know, like strong EC key, you could use a passphrase or something. But again, like the user, you're adding user complexity here. Yeah, you could be around somewhere and you lose your keys. So all this said, let's jump into my solution, or the solution that I'm going to describe here. Which sort of takes the multi-sig premise here, right? Which is that you have two participants, you know, if they both kind of mix their randomness in, then you can avoid biasing. And the trick here is that for purposes of key exfiltration through this nonce side channel, you actually don't really need to worry about key bias. I guess you do it at key setup time, right? You want to make sure that your key isn't, you know, compromised and not coming from some sort of Debian random number generator that only has 32 bits of entropy or something like that. But empirically, it appears that you don't really care about small amounts of bias in your key. It's really only the nonce where you have this crucial, like even a small compromise is the end of the world kind of situation. So what we're going to do is do kind of a weak form of multi-signature where rather than combining the keys, we're just going to combine the nonces at signing time, okay? And then the cool thing here is that because the nonce is ephemeral, it can just be thrown away after use. So you can have a host computer that generates randomness in some way, and it doesn't need to be good randomness. It just needs to be basically unpredictable. But it can be biased, and it can have a reasonably small state space and things like this. The host computer can generate this, pass it to the hardware wallet. The hardware wallet produces a signature by mixing in this randomness in some way that the host is able to verify, which I'll talk about. and then the host just throws away the randomness. So that's what we're going to get into. Cool. So we call our solution anti-exfil or anti-exfiltration. A long time ago, we called it anti-klepto, which was I thought a much cooler name. But kleptography is a bit of an obscure term. I just checked on Wikipedia. Apparently, it dates to a talk at Crypto in 1996. Cryptography is the art of the field of cryptography related to trying to steal information, maybe through like secret side channels and stuff. And the whole Wikipedia, I encourage you to check this Wikipedia page. It's just like really obscure 90s like cypherpunk stuff. It's pretty cool. But we changed the name to exfiltration because exfiltration is a more widely understood term, and it captures more specifically what we're trying to do here. So as I said, right, the premise here is that the host is going to provide a random challenge to the hardware wallet. And the hardware wallet will take that random challenge and it will tweak the nonce that it generates in a way that commits to the challenge. And it does this in a way that the host can verify this tweak. And then we're going to do this tweak in a way that completely re-randomizes the nonce. So it eliminates any sort of bias. And then we're going to do this similar to with deterministic nonces. We'll stick a hash function in there so that even if the host randomness is kind of biased in some way or not very high quality randomness, we still do a complete re-randomization. And so the premise here is that as long as the attacker hasn't compromised both the hardware wallet producing the original untweaked nonce and the host choosing its randomness, then we can't extract any information from here. So let me actually jump to the very end now and just kind of wrap up with that. And then you may have saw Chris just scrolled through is scrolling through these two bonus slides here, which cover the technical issues here. And then we can double back to that if people have more specific questions. But I just want to give on a high level, I want to give a picture of everything here. So to wrap up, since I am at about 20 minutes here, we have a blog post here. You can just Google anti-exfil, and this blog post will show up, describing basically everything that I just described in this talk. It's got a little bit more technical details. We've implemented this on the Blockstream Jade, which is a hardware wallet that we produce. And we actually use this technique to communicate with the host computer to make sure that even if the Jade's nonce generation code were somehow compromised, that there would be no way for us to exfiltrate keys. I also, when I was researching stuff for this talk, I found an old implementation I did in 2017, trying to insert this into a project called Open Timestamps, which uses commitment schemes. The idea behind Open Timestamps, if you're not familiar, is that you can take whatever data you want to prove existed before a certain date. You can commit to it in a giant Merkle tree, and then you can put a commitment to the Merkle tree root somewhere on the Bitcoin blockchain. And since the Bitcoin blockchain has pretty strong timestamps that are extremely expensive to forge, you can treat the commitment that you get from there. You basically get a commitment to your data in the Bitcoin blockchain, proving that the data existed before that Bitcoin block, which gives kind of a one-way proof of timestamping, basically. So it's a very useful general purpose tool. And one thing I was playing with in 2017 was using this nonce tweaking trick to say, well, what if we tweak the nonce not by some random data, but by some data that I wanted to timestamp? Then you can actually get this anti-exfil technique. And as a side effect, if you chase through all the commitment structures here, you wind up with a blockchain that has a signature on it, and the signature nonce itself is a commitment to a Merkle tree that contains commitments to all sorts of documents. And so for free, you get open timestamps kind of behavior, and you can't even like really distinguish open timestamps commitment from anything else. So we can get the blockchain space usage down from 32 bytes to 0. So I just thought I'd mention that because it's exactly the same techniques, a slightly different application. And it's a neat piece of history from the anti-exfil thing. So that is my presentation. I guess we can do Q&A.
Yeah, so the reason why I wanted to bring you to the Silicon community here is that we're increasingly talking about how do we trust hardware where there might be questions of trust. So what are different methods of doing this? And when you first introduced me to this concept, probably around 2017, I was just, I was enamored of it because all the other solutions felt like would be very difficult to get down to the silicon level. Because of, as you said, the complexity of ZKPs, and plus that whole area has been evolving so fast. I don't even want to commit to which ZKP technique because it seems like, oh, this is the best one. It'll be good for years. Oh, nope, wrong. Another year. We got an even better one that's 10 times more efficient. So I just felt this was an interesting, elegant way of trusting the hardware less. But for it to really work, it's not just say implement it on MicroPython, or I'm not sure what Jade uses, but really should be all the way down to the trusted element, which means that we need to have this nonce channel somehow, and our protocols need to have those.